Hi, everyone. My name is Brent Biginger, and I'm a database engineer in the AFT org, Amazon Fulfillment Technologies. And I'm going to talk about our migration from Oracle to Amazon Aurora with Postgres compatibility, and specifically for our inventory management systems. So what we're going to talk about today is I'm going to give a little bit of information on Amazon Fulfillment Technologies. That is the warehouses basically in Amazon. We're going to talk about the technical challenges that we faced preparing and for the migration. And then I'm going to talk about how we ultimately performed the migration of all of our FC database systems to Aurora Postgres. So Amazon Fulfillment Technologies encompasses all the operations that happen within fulfillment centers. We have over 350 FCs worldwide, and they range from tens of thousands to even over 1 million square feet. And they employ hundreds or even thousands of associates depending on the time of year, for instance, Q4 time. And in our sortable FCs, there's miles of conveyances transporting items and packages throughout. For example, in one of our largest FCs, it's over 1.2 million square feet in size, which is about 28 football fields, and the size of 6 times the largest Costco. So you can see how expansive the FCs are physically, as well as the number of employees and processes that have to be supported by these databases and our services. One of the things I wanted to talk about a little bit, you can see this is a picker picking items from the shelves. There's a great deal of interaction between physical machines, such as like the handheld scanner that he's wearing or has, people, as well as automated processes. And so inventory drives all of this. It's the master authority for all of the items in the FC. And with this, response times are very important for us because we need to know the state and location of inventory at any given time. SLAs are very important. The same is true for this pack station here, as associates are pulling items from the totes, packing them, and putting them into boxes to put along the conveyances. Any slowdown there impacts the associates. This is the SLAM line. And so this is where split-second response time is very, very important because this is an automated process. And between the time you can see that red scanner has to scan the package, the box, and then make decisions based on what's in the box and the best method to ship this. And then it ultimately print and slam the label on here. All of this has to make calls to inventory, amongst a lot of other services are shared between this process. But this is one example where any slowdown in latency here, it really impacts the FC. So talking about some of the challenges, the number of Oracle databases that we had to migrate was about 350. And so we knew very early on, obviously, we'd need a high degree of automation to do this. And just to note, these are some of the oldest databases in Amazon. They've had 20 years of wrenching on these Oracle databases for optimizing the queries and the database and kind of squeezing every ounce of performance out of here for this. So it was a tall order to migrate away from the database platform. And it had to be done with minimal downtime requirements and along with dozens of different services. And there were a lot of dependencies that were not known. We knew most of the dependencies, but there are, over the accumulation of 20 years, not everything was quite known, what services access which tables or views and things like that. There were some outliers. So that was one of our early tasks, and we'll talk more about that. And we already discussed how and why latency and call requirements were important to us. So at a big 50,000-foot view, this is kind of what AFT looked like prior to migration. We had Oracle databases, one per FC, and 350 plus of them. And each of different teams and services made calls directly to the database, as well as to inventory and a combination thereof. So we had a lot of services accessing directly to the database and some making service-to-service calls as well through inventory and amongst other services. This is a very high-level picture. Some of the other challenges that we had when it came time to scaling, for instance, databases, was the ability to scale. And this was due to our FCs and our systems requiring the use of some custom hardware. At Amazon, we had small, medium, and large size hardware, but we had really outgrown that. And in fact, we had to go through a lot of effort to make sure that we had a custom built extra large database just for our team because we had outgrown the other hardware. So being able to scale that and get those in place and scale for peak periods was a challenge. One of the other aspects of availability was that if we had in Oracle fast start failover, we had a reader node if we had a failure on our primary and we failed over, that all happened. But if we had to replace the hardware or repair it, that could take hours or even longer to get us back to a high availability state where we have a primary and a standby replicating in real time. So there was a longer time to recover and get back to that HA state. And of course, with this hardware, being able to forecast based on our shipment volumes and being able to order the hardware and then provision it took quite a long time. In provisioning, we had to prepare the hardware, restore the database completely, which could take some time depending on the size of the database, and then get it into a operational state and then swap it in to be replicating in real time. So there was a lot of operational burden when it came to scaling the fleet with on-site, on-premise databases. One of the things that AFT, as well as all of Amazon, really did was take a look, and SDE teams looked at what their preferred persistent store should be and came with what is a purpose-built relational store, purpose-built databases. So our organization looked, and for inventory, the ideal persistent solution was indeed relational, but a lot of other services went to key value stores such as Dynamo and other places, which made more sense for their services. So why did we choose Aurora Postgres? There's a lot of reasons, and some of them are listed here. For instance, high performance. We'll talk about some of those a little bit later, but there's a lot of advantages that Aurora Postgres has over, for instance, Community Postgres. The way that the storage engine performs and, for instance, handles checkpoints, which impacts different latencies. And basically the checkpoints, for instance, have been pushed down to the storage layer, affecting recoverability and failover speed. That was another advantage that we looked at, was the ability to recover and to get back into high availability. And the failover times from Oracle were 2 to 3 minutes, which is pretty quick, but moving to Aurora Postgres has a lot of advantages in the way that it recovers and the speed to failover to the reader instance and become a new writer. We see less than a minute typically, and that's a big difference between what we saw and get our FCs back to working on Aurora Postgres. Obviously, the feature parity going from Oracle to Postgres itself, which is probably the closest database that's similar to Oracle in terms of not having to rewrite a ton of different things. The scalability for Aurora Postgres was something that was important to us, and being able to scale out horizontally on the reader instances. And having those reader instances have single-digit replica lag because of the way that the Aurora storage engine is designed. Similarly, because of the Aurora storage engine, how database backups are taken at the storage nodes. So we don't have to schedule backups, and we don't have to take a hit of having that I/O performance on our database head nodes. And the advantage of being able to leverage full volume production copies to do lots of non-prod testing, and we're going to talk more about that as well. Talking about the Postgres migration itself, I'm going to walk through some of the preparation and then the actual cutovers, and then also kind of living in Postgres afterwards. So one of the important decisions that we made was for our AWS accounts was to separate prod and non-prod accounts, just as a best practice to follow. The ability to leverage the power of having reads go to a reader fleet was in a design pattern that allowed us to ensure that we could scale. So we spent a lot of time, and our service team spent a lot of time identifying the calls that could be made and pushed off to readers to allow us to scale very easily, to allow us, if we needed to have additional readers, that could be done behind the scenes. We also made a lot of use of snapshots and clones. This helped us in the initial functional testing and continues to help us quite a bit in our load testing environments, to be able to restore a snapshot, full volume snapshot, and to be able to take baselines and do A/B testing after changes are made, whether those changes are application-based or upgrades to the database. Having proper load testing environments has proved really invaluable to us to be able to predictively deploy software and upgrades into production, into a large fleet. Another early on decision that we made was to ensure that we had encryption in transit and at rest. And this wasn't the case in Oracle, but is the right thing to do. And to leverage APIs and CLIs that AWS provided and plan for this automation. We'll talk a lot more about automation in later on. One other thing that wanted to note is that we performed a lot of non-prod cutovers and cutbacks prior to our first FC cutover. This was also just invaluable to learn every time. Multiple iterations of doing this. Every time we really learned quite a bit, and it helped us to be successful the first time in our first FC without issues and beyond that. So talking about really some of the differences and considerations to make when we're moving from Oracle to Postgres, these are some of the things that we had to take a look at. And one of those was the differences between timestamps and time zones in Oracle versus Postgres. For instance, a lot of our code was based on Oracle sysdate and to persist dates. That's based on a server's time zone, essentially. And in Postgres, it just functions differently, where the client determines the date that is persisted into the database. So we had to go through and look at all of our tables and the dates that we intended to persist, and to make sure that we had the data types correct. Another difference is in partitioning, was a major difference between how Oracle and Postgres function. We migrated to a version of Postgres that currently doesn't support global unique, primary unique keys across partitioned tables. And this was important to note because in Oracle, a partition table in our schemas typically had a primary key that was global, and then other indexes that were at a local partition level, but not having the global uniqueness, we had to do some investigation, and our development teams just had to validate that they could accommodate this difference. The differences in the version that we migrated to in Postgres 9.6 it uses an inheritance type of partitioning, which is really based on inheritance and child tables and use of triggers to put the data in different child tables that they need to be in. This improves a lot in Postgres 10, where we have declarative partitioning. This is much more like what we'd expect in Oracle, for instance. And then in Postgres 11, there are a lot of additions to partitioning schemes, but this was a major difference because we did make use of partition tables quite heavily to keep our data lifecycle at a minimum, because just to keep the data relevant to what's really needed. Another consideration to take into account is that the collation differences between Oracle and a standard spinning up a Postgres database. And the collation is based on text columns or how they are sorted. So for instance, how you sort and order by different upper or lowercase or special characters. And if you, in English US, it's going to order things differently versus a collation, a C collation, where it's going to order capitalization, for instance, above lowercase or above special characters, and then numerics. The DMS, the Database Migration Service, also will depend on this. So we'll talk more about that, but the data validation piece of it was very important because it's going to order and make sure row by row we are comparing that we have the exact same values from source to target. As I mentioned, our dependency analysis was really one of our first tasks to kind of unsort all of the dependencies between these shared objects. As you saw in the high-level view, there are a lot of different services and service teams that were looking at shared tables. They both looked at these tables, they interacted, sometimes they wrote data in the same tables or views or sequences, and we needed to make sure that we understood all of these dependencies to know how to break things apart and migrate, because a lot of these service teams, like I said, didn't necessarily migrate to the same database or even data store, moving to other data stores like Dynamo. There was also a large web of materialized views that were cross-database. This was more of domain data and how it has been propagated throughout Amazon over years and years. So this web had to be untangled, and working with teams to ensure that they had another way to obtain this domain data as well. And then the data warehouse jobs, typically running on a reader instance, to ensure that we understood what was running and what needed to be continue to function and to feed data into the data warehouse. So we also needed a way to absolutely capture all of our SQLs to understand these dependencies. And what we did was look at $SQL and SQL area, for instance, views into Oracle's memory to see the SQL. So we built tooling around this, and the tooling went and sampled these periodically to ensure that after SQL's executed and they're in those memory areas, that we were able to capture those so that we fully captured all of these dependencies. And service teams could analyze this and understand the service calls that they're making. In some limited cases, we also used the use of logon triggers, which also provided an additional level of help to understand all of these dependencies. So talking about the migration itself, as I mentioned, we knew that we needed a very high degree of automation. And so in order to launch our databases, we built tooling to allow us to do that. And to walk through some of the steps that were involved in this to capture all of our database instances in metadata to make sure that we understood what was there, what we were spinning up, what instances, what the host size was, what the version was, and to ensure that we created reserved instances just as a frugality measure to make sure that we are kind of doing the right thing. Finally, kind of creating the databases. Once those are done, the tooling allowed us to then onboard ETLM jobs, and from there ensure that we onboard our scheduled jobs. So for instance, being able to schedule a rolling partition job to drop off the oldest partitions and add new ones dependent on each table's data lifecycle. And then we integrated with CloudWatch metrics, making sure that we monitor these systems to create that monitoring and alerting to ensure that obviously our databases are healthy. Finally, kind of creating the application DDL, the application schema, and then to be able to kick off the DMS service. Some of the requirements that we had were obviously to not impact our FC operations. We had to be cautious to not overwhelm the source side Oracle database while we were transferring data. And so mitigations in place to make sure that we didn't cause any harm there. And to fit into a short downtime window, typically within about 1 hour to 2 hours, ensuring that all of our performance was on par or better than Oracle. In terms of the migration itself, to make sure that we perform our full load and ongoing replication, but at the same time, we are validating data as it comes across the wire. And so DMS does provide that with us. And that was very important to make sure that we can fit in our cutover window. If we had to validate our data only at cutover time, we never would have been able to fit into our windows in some cases, as well as having alarming and monitoring to ensure that those processes are up and running, because we would typically start this a week or two ahead of time, make sure that we're in replicating mode, everything is flowing as normal, and then it's just going to sit there until the scheduled cutover date. We did have to schedule these very highly with our FCs because typically around a shift transfer time or a downtime that no one is working at the FC. Additionally, as I mentioned, we had a high degree of automation, and I'll talk more about this and how our service teams built a framework to support that. So the basic data migration starts with using the AWS schema conversion tool to obtain the DDL. And this is the tables, views, sequences, etc. This was kind of a starting point. We had some application functions and some triggers that the tool didn't automatically convert. For us, it was a smaller subset because the databases are used as more of a persistent store than persisting the application logic in the database. But once we did that and obtained the schema, then using the database migration service to perform a full load from our source Oracle database, ongoing change data capture, CDC replication into the Postgres database. One of the things that we noted very early on was this wasn't going to be a zero downtime migration. So it allowed us to make some decisions that would have been more complex if we had said it could be very, very minimal downtime migration as opposed to having an hour. We focused on mostly a lift and shift where possible, and tried to limit our scope to that. We also started with several pilot FCs, and in these early on ones, there was limited automation, but in order to learn and progress, these pilot FCs were, we did many pilot FCs before we were in full automation mode. One of the things that we did was decide to migrate our largest database very early on in our migration cycle. This proved to be very useful because it gave us the ability to see any issues on our largest systems early on and to focus on those and to be able to put all of our attention and time into a single database if we had some problems, as opposed to getting towards the end of our migration cycle where we have our largest databases and FCs, and then we had to work on this across many different databases. So going through a peak period with our largest systems on Aurora Postgres, we had some learnings, but we were able to dedicate some time and fix those properly going forward and make the rest of our migration very successful. And then we're going to talk about our full migration automation coming up here in detail. This is a workflow engine that the service teams developed for the migration of databases as well as all of the service components. So it's driven by a DevOps operator or DevOps operators using CLIs or web interface and a system description which basically invokes different components and tells what to do. It uses a requires, provides, and invokes model. It's dependency driven. It also supports parallel execution of different steps though. And those are based on Amazon's simple workflow. And once when the system description is iterating through and calling different components, Java components, DMS, SQL interface components, they are calling these, making calls to different services. For Java components using inventory services or kicking off the DMS service or stopping the DMS service, making networking changes, making schema changes to the Aurora databases themselves. And so what we were able to achieve was a high degree of automation of this, where multiple DevOps operators were driving this without database or service teams being a part of this unless there was a problem. And so at our maximum, we were migrating over 30 instances per day in some cases throughout the peak of this migration cycle. So now that we've migrated, talking a little bit about some of the lessons learned and kind of living in Aurora Postgres. Starting with DMS, one of the things that we really learned early on was that some of the difficulties using DMS actually came from our schema itself. Although most tables, for instance, had primary keys, there were a small number that didn't. And this is absolutely required for lobs, but also for data validation. And that was the key piece for us. And we looked at a couple of different ways to go about this, but ultimately, for most cases, we went back and fixed our source schema to ensure that we had PKs or UKs there so that we could have inline data validation, which was quite important. We needed to identify the tables with lobs, with large objects, and the DMS tool provides full lob mode and limited lob mode. Full is able to migrate lobs of any size, but it doesn't really know the complete size of the large objects. So it has to go piece by piece, and it can be quite slow. Limited lob mode, on the other hand, we are able to determine the size of the lobs and be able to load those in bulk. So it's much faster. And then the inline blob mode is kind of a hybrid of both of those. It seems a little bit silly, but having a very large replication instance actually saved us a lot of troubleshooting and headache, as opposed to trying to very closely size this to what we think we need. Saved a lot of time to just have a larger instance and to avoid a lot of those troubleshooting tasks. Monitoring, as I mentioned, of this was very important to ensure that on cutover day, we were 100% ready. That something hadn't happened in terminating our replication instance or any other piece of the replication. And another thing that we did, which was proved quite helpful, was to have a heartbeat table for each DMS task. And what I mean by that is when we performed a cutover, to ensure that we had every piece of data, part of our process was even to, when we had shut down all services, we even renamed tables to ensure that no more data could be inserted into our source system. But to make sure that we had all of our data, we kind of went a step further and placed this heartbeat table and added a dummy record to ensure that once that dummy record had made it over to the target database, we then had all of our data for each DMS task, and we could proceed quickly in the migration. And then just as a matter of procedure to ensure that all of our triggers were enabled after stopping DMS tasks and the DMS validation. So additionally, one of the other things that really helped in our migration was to really take a look at the life cycle of our data. As I mentioned, we made heavy use of partition tables, and to really dig deeper into understanding if we really needed a 90-day retention for some of this data. And in a lot of cases, we didn't. These were things that were built up over time, or maybe not well understood or researched when these tables or data retention was established. But in any case, we were able to reduce the amount of data that we had to transfer and that we had to maintain. And so that helped us, in the migration as well as the size of our new Aurora Postgres databases. Other things that our service teams did very well was to instrument their code by using hints. And so the hints provide an exact identifier into the code as to what APIs are being called. So it allows us to very quickly and easily identify SQL and even look it up in code repository to find the exact SQL and where it's coming from, and to be able to have this dialogue with service teams and DBAs very quickly and easily, so that we're not searching for the SQL, how it looks in the database versus how it is in code. This has proved to be a very good advantage here. Also, to identify that sequences work a little bit differently in Oracle and Postgres, and Oracle has a global sequence cache, whereas Postgres, it's per connection. So in one particular application, it did matter the sequence order. And we found in testing, typically in Oracle, having a large cache helps with performance considerably. However, in Postgres, we saw less than about a 2% difference, even under heavy workload, where we have basically no cache, and it treats the sequences much similar as it was in Oracle. And this was advantageous because our service teams would have had to make a lot of changes to change application logic and to change the logic for their clients. The use of SSL and specifically verify full allows us to end-to-end make sure that the client and the endpoint, the database, understand who's talking to who. And to ensure that nulls are treated a little differently in Oracle versus Postgres, such as in Postgres, it is stored as an empty string, whereas nulls and empty strings are the same in Oracle. Looking at exception blocks, and for us it was looking at these blocks in triggers. An exception block consumes transaction IDs, and we'll talk more about this when we're going to talk about vacuum. And even when the exception isn't raised, the trigger is fired and we consume transaction IDs. We didn't want that. It's very important. So raising notices or errors doesn't provide that behavior. Also, idle transactions we have to be more aware of those in Postgres. So if you start a transaction and make changes to a number of rows, and then this transaction sits there idle for whatever reason, it's preventing dead tuple cleanup and multi-transaction cleanup in Postgres. So just a difference in engines, how we have to be aware of this. Postgres 9.6 and later provides an idle in transaction session timeout parameter to have a maximum threshold on that, where it will terminate the connection when you've reached that threshold. And the use of global temporary tables, but global temporary tables are not present in Postgres. If we use temporary tables, there are different methods to do that, but creating and dropping those creates a lot of churn in the database where we're creating the table, filling it with data, and then dropping it at the end. So there are other ways to do that, to delete the rows instead as well. As I mentioned, and this is where we're talking about the transaction IDs, the maximum unvacuumed transactions is a hard limit of 2.1 billion. And we don't want to hit this. This is where Postgres is going to have to single-threadedly vacuum the database, and no operations can occur while this is happening. So the maximum used transaction IDs, CloudWatch metric monitors for that. This is really critical to ensure that we're nowhere near that limit and to have monitoring and alerting. A couple of catalog views, the pgstat all tables, for instance. This is one of a number of places to look for more detailed and granular view of how your auto vacuum is progressing, and to make sure that everything is healthy, because it is so critical in Postgres. And looking at the live and dead tuples, the auto vacuum date, and looking at potentially a ratio, all of these types of monitoring really help to ensure that the auto vacuum is progressing as we would expect. There are dozens of auto vacuum and vacuum parameters. Just to be aware that the defaults really can't accommodate all situations. So these are a few key ones to take a look at, but really it's really important that auto vacuum is tuned and executing correctly for the health of the database and client latencies. One other thing to note when creating tables is the fill factor. This is how tightly that the pages are going to be packed with rows of data. And if we have an insert-only table, the fill factor of filling it to its maximum 100% is just fine. But if you have a heavy DML table where you're inserting, updating, and deleting, definitely going to want to take a look at reducing that and finding the optimal threshold for that fill factor to allow updates, for instance, to place the updated copy of a row in the same page as the original, as opposed to placing it on a different page. Wanted to take a little bit of time and talk about the performance insights. This has been a real big benefit for our team to be able to look at the average active sessions compared to CPU, and to take a look what everything is waiting on, all of the wait events in the database, and to understand what is happening, or for incident management, going back and looked at what happened has been particularly useful. Performance Insights is able to give you 7 days worth of data retention for free, and then beyond that to 2 years. of keeping this to look at investigative what happened or what your databases were waiting on. In addition to that, more recently introduced are performance insights counter metrics, which are a little bit more of a view into the database and some of the things that are happening, such as the committed transactions per second or active transactions, a whole wealth of information on what your database is doing kind of at a high level. And again, looking back in terms of any issues to try to root cause things. As we talked about using CloudWatch dashboards and alarms, making use of key metrics that CloudWatch provides for CPU or connections or replication lag to reader fleets, availability and things like that. They are continuing to add CloudWatch metrics all the time, but the basic CloudWatch metrics are extremely useful to get an overall instance health. And we also used the AWS Cost Explorer in order to really dig in deeper once we've migrated to Postgres of where our costs are. For instance, understanding more in detail of how a backup retention affects how much we are charged monthly, because in the end, we do look at frugality and to use what AWS services effectively. So kind of wrapping up, the benefits that we've seen for AFT is that we were able to, performance-wise, scale to our largest workloads. And again, that wasn't necessarily easy for even classic Oracle classic Amazon hardware and the workloads that we had, as well as the latency requirements and to be able to perform at or better to Oracle. In scalability, now we're able to scale up and down in minutes. It really is seamless vertical scaling, almost seamless vertical scaling, I should say, but seamless horizontal read scaling as needed. The benefits of faster failover, taking minutes, and then getting back to that high availability state in minutes, like I talked about after a hardware state, just using the cloud to swap in more hardware that's readily available. We talked about the hardware management. It has really taken the burden of managing hardware off of our database team and to make better use of our team for other tasks such as automation and using the AWS APIs and CLIs to manage processes. For instance, creating processes to do upgrades across hundreds and hundreds of databases is something that our team recently rolled out and has been a real benefit to us. Building databases from snapshots to be able to do load testing, as we talked about, and that we don't have any more Oracle costs. So that's it. Thank you very much for your time.